Hello children, in this video I am going to explain about ionic equilibrium in solution. When equilibrium is established between ions and unionized molecule, this type of equilibrium is known as ionic equilibrium. One example is given here. As you know that this symbol represents the equilibrium condition. Before we start this topic, we have to know about strong and weak electrolytes. According to Michael Faraday, substances that can be classified into two categories based on their ability to conduct electricity. Number one, electrolyte, and number two, non-electrolyte. Electrolytes are the substances which conduct the electricity in their aqueous solution. For example, all the acids, bases and salts, they conduct the electricity in their aqueous solution. Non-electrolytes are the substances which do not conduct the electricity in their aqueous solution like sugar solution. Electrolytes may be further classified into two subcategories, that is strong electrolyte and weak electrolyte. Strong electrolyte on dissolution dissociate completely like NaCl. Weak electrolyte dissociate partially on dissolution. For example, acetic acid. Acid, bases and salts are considered as electrolyte. Now we will discuss some common properties of acids, bases and salts. As you know that acids are sour in taste, they turn blue litmus into red. Acids liberate hydrogen when react with metals. This reaction you have done in 10th class. For example, when zinc react with H2SO4, it will give ZnSO4 plus hydrogen, H2 gas will be evolved here. Bases taste bitter and feel soapy. Bases turn red litmus blue. When acid and bases are mixed in right proportion, they react with each other to give salt like sodium chloride. Dissolution of NaCl in water. Sodium chloride is formed by reaction between hydrochloric acid and sodium hydroxide. The reaction can be written as like this. HCl when react with NaOH, it will give NaCl, sodium chloride. It exists in solid state as a cluster of positively charged sodium ions and negatively charged chloride ions, which are held together due to electrostatic interactions between oppositely charged species. The electrostatic interaction between ions are inversely proportional to dielectric constant of medium. When sodium chloride is dissolved in water, electrostatic interaction reduced by factor 80, and this facilitates ion to move freely in the solution. As we know that dielectric constant of water is 80, therefore the electrostatic interaction will reduce by the factor 80 and it causes the free movement of ions. Now this can be explained with this diagram. In this diagram, the positive and negative ions, that is Na plus and Cl minus, are given here. Cl minus is represented by the green colored circle and Na plus is represented by yellow colored circle. When we dissolve NaCl in water, the water molecule attract the oppositely charged ions. Therefore, these ions are separated from each other and they can move freely. In this diagram, you can very easily see that the water molecule will surround the oppositely charged ions, and now the oppositely charged ions can move freely. Here we use two terms, dissociation and ionization. So let me clear the difference between dissociation and ionization. First, dissociation is the process of separation of ions in water which already existing as such in solid state of the solute, like in NaCl. As you know that in NaCl, Na plus and Cl minus ions are already exist, and when we dissolve the NaCl in water, these ions are just get separated from each other. In ionization, a neutral molecule splits into charged ions in the solution. For example, HCl, hydrochloric acid. Hydrochloric acid में एज सच कोई भी पॉजिटिवली चार्ज या नेगेटिवली चार्ज आयन प्रेजेंट नहीं है जब ये न्यूट्रल मॉलिक्यूल है, बट जब हम इसे डिसॉल्व करते हैं वाटर में तो ये H प्लस एंड Cl माइनस में डिसोसिएट हो जाता है. सो दिस इज नोन एज आयोनाइजेशन. आई होप द डिफरेंस बिटवीन डिसोसिएशन एंड आयोनाइजेशन इज क्लियर हियर. और इस चैप्टर में हम इन दोनों वर्ड्स को एक जैसा यूज़ करेंगे, मतलब डिसोसिएशन और आयोनाइजेशन दोनों वर्ड्स को हम यूज़ कर सकते हैं फॉर द फॉर्मेशन ऑफ आयन्स इन सॉल्यूशन. Now we are going to discuss some theories about acids and bases. The first theory is Arrhenius concept of acids and bases. According to this theory, acids are those substances that dissociate in water to give H plus ions, and bases are those substances which produce hydroxyl ion. जो भी सब्सटेंसेस डिसोसिएट होकर H प्लस आयन देते हैं उन्हें हम एसिड्स कहते हैं, और जो सब्सटेंसेस हाइड्रोक्सिल आयन OH माइनस आयन देते हैं उन्हें हम बेस कहते हैं. द आयोनाइजेशन ऑफ एन एसिड HX कैन बी रिप्रेजेंटेड बाय द फॉलोइंग इक्वेशन. The acid will dissociate into H plus and X minus, and this can be written like this also. HX plus H2O gives H3O plus X minus. This is hydrogen ion. This is hydrogen ion, and this H3O plus is known as hydronium ion. As we know that a single proton is very reactive and cannot exist freely in aqueous solution, thus it bonds to the oxygen atom of a solvent water molecule to give a trigonal pyramidal hydronium ion H3O plus, and it can be written like this, that H2O plus. The shape of this H3O plus will be trigonal bipyramidal. Now, a base molecule like MOH ionizes in aqueous solution according to the equation, that is MOH gives M plus OH minus. The hydroxyl ion also exists in hydrated form in the aqueous solution. There are some limitations of Arrhenius concept that this is applicable only to aqueous solution. मतलब अगर हम HCl को गैसियस स्टेट में लेते हैं तो हम उसे एक एसिड कंसिडर नहीं कर सकते. जब तक हम HCl को वाटर में डिसॉल्व नहीं करेंगे वो H प्लस आयन नहीं देगा. सो this concept is limited to the aqueous solution only. It does not account for the basicity of substances like ammonia, which do not possess hydroxyl group. As we know that according to this concept we can explain the basicity of NaOH, KOH, etc. But ammonia also shows basic nature. तो इसको हम यहाँ एक्सप्लेन नहीं कर सकते क्योंकि अमोनिया में कोई भी OH आयन प्रेजेंट नहीं होता है. सो दीज आर द टू लिमिटेशंस ऑफ Arrhenius concept. To overcome these limitations, few more concepts are given. उससे पहले हम हाइड्रोनियम आयन और हाइड्रोक्सिल आयन्स के बारे में पढ़ते हैं. Hydrogen ion by itself a bearer proton with very small size, that is 10 to the power minus 15 meter, and intense electric field bind itself with water molecule at one of the two available lone pairs on it, giving H3O plus. The species has been detected in many compounds like H3O plus Cl minus in the solid state. In aqueous solution, the hydronium ion is further hydrated to give species like H5O2 plus, H7O3 plus, H9O4 plus. Similarly, the hydroxyl ion is hydrated to give several ionic species like H3O2 minus, H5O3 minus, H7O4 minus, etc. Here, a diagram of H9O4 plus is given. With the help of this diagram you can very easily understand that how H plus ion get hydrolyzed or form the bond with water molecule. Next acid base theory is Bronsted-Lowry acids and bases theory. According to this theory, acid is a substance that is capable of donating a hydrogen ion, and bases are substances capable of accepting a hydrogen ion. In short, Acids are proton donors and bases are proton acceptors. For example, when we dissolve NH3 in water, we can express it with the help of this equation. NH3 in presence of water convert into NH4 plus ion and OH minus ion. The basic solution is formed due to presence of hydroxyl ion. In this reaction, water molecules act as a proton donor and ammonia molecule act as a proton acceptor and thus called Lowry-Bronsted acid and base. So, with the help of Bronsted-Lowry theory of acids and bases, we can explain the basic nature of ammonia, that is NH3. NH3 will act as a base, water will act as an acid, water will give one proton to NH3 and it will convert into NH4 plus ion and OH minus ion will form, and due to the formation of OH minus ion or hydroxyl ion, the solution becomes basic in nature. In the reverse reaction, H plus transferred from NH4 plus to OH minus. In this case, NH4 plus acts as a Bronsted acid while OH minus acted as a Bronsted base. Look the reaction again. If we consider the backward reaction, then NH4 plus will donate one proton to OH minus ion. So NH4 plus act as an acid and OH minus will act as a base. The acid-base pair that differs only by one proton is called a conjugate acid-base pair. Therefore, OH minus is called the conjugate base of an acid H2O and NH4 plus is called conjugate acid of the base NH3. Again, look at the equation. We can very easily find it out that there is a difference of only H plus in NH3 and NH4 plus and in H2O and OH minus. So these are the conjugate acid base pair. There are some important points to be remembered. If Bronsted acid is a strong acid, then its conjugate base is a weak base and vice versa. It may be noted that conjugate acid has one extra proton and each conjugate base has one less proton. For example, if we compare NH3 and NH4 plus, then NH4 plus will act as an acid and it has one extra proton, or NH3 which act as a base have one proton less than the acid. Ionization of hydrochloric acid in water. This is the another example of conjugate acid base theory. When we know that HCl act as an acid by donating a proton to H2o molecule which act as a base. When we dissolve the HCl in water, HCl will donate one H plus to H2o and it will convert into Cl minus ion, and this will be the conjugate base of HCl. H2 will accept one H plus and it will be the conjugate acid of H2O. Let's take one more example to understand Bronsted-Lowry concept of acids and bases. Ionization of hydrochloric acid in water. Hydrochloric acid act as an acid by donating a proton to H2O molecule which act as a base. HCl will donate a proton to H2O and convert into Cl minus, and H2O will convert into H3O plus. Here HCl and Cl minus are conjugate acid base pair and H2O and H3O plus are conjugate acid base pair. Water acts as a base because it accepts the proton. The species H3O plus is produced when water accepts a proton from HCl. Therefore, Cl minus is a conjugate base of HCl and HCl is the conjugate acid of base Cl minus. Similarly, H2O is a conjugate base of an acid H3O plus and H3O plus is the conjugate acid of base H2O. Here, with the help of these two examples, NH3 and HCl, we can very easily conclude that water can act as an acid and a base. There are some limitations of Bronsted-Lowry acids and bases theory. The number one is the protonic definition cannot be used to explain the reactions occurring in non-protonic solvents like CuCl2, SO2, N2O4, etc. It cannot explain the reactions between acidic oxides like carbon dioxide, sulfur dioxide, etc. and the basic oxides like calcium oxide, magnesium oxide, which takes place even in the absence of the solvent. One example is given here. When calcium oxide reacts with sulfur dioxide, CaSO3 is formed. There is no proton transfer in the above example. The third limitation is substances like BF3, AlCl3, etc. do not have any hydrogen and hence cannot give proton but are known to behave as acids. Now we will solve some questions based on Bronsted-Lowry acids and bases theory. The first question is, what will be the conjugate basis for the following Bronsted acids? HF, H2SO4, HCO3 minus. As we know that Bronsted acid will have one more proton than its conjugate base. Now we have to find out the basis for the given acid. So we have to remove one H plus from the given molecules or ions. So from HF, the conjugate base will be F minus. H2SO4, the conjugate base will be HSO4 minus. And from HCO3 minus, when we remove one hydrogen, then we will get CO3 2 minus. The next question is, write the conjugate acids for the following Bronsted bases. Okay, now we know that to convert a base into Bronsted acid, we have to add one proton to it. We will add a proton to it. NH2 minus, when we will add a proton to it, it will convert into NH3. NH3, when we add a proton, it will convert into NH4 plus. HCOO minus, when we add a proton, it will convert into HCOOH respectively. The next question is, the species H2O, HCO3 minus, HSO4 minus and NH3 can act both as Bronsted acids and bases. For each case, give the corresponding conjugate acids and bases. How we will solve it? Again, the very simple concept. Whatever the species is given to us, we just have to add a proton to get the conjugate acid. And we will remove one proton to get the conjugate base. So the answer is given here. From H2O, the conjugate acid will be H3O plus and conjugate base will be OH minus. We will balance the charge accordingly. HCO3 minus, when we add the H plus to it, it will convert into H2CO3. When we remove one H plus, it will convert into CO3 2 minus. One more negative charge it will carry when we remove one positive charge from it, one H plus from it. HSO4 minus, when we add one H plus to it, it will convert into H2SO4. And when we remove one H plus from this species, it will convert into SO4 2 minus. NH3, when we add one H plus to it, it will convert into NH4 plus, and when we remove one H plus, it will convert into NH2 minus. These are very simple questions and can be solved very. According to Lewis acids and bases theory, acids accept electron pair and base donate electron pair. We can understand the concepts of Lewis acids and bases by taking a very simple example, that is reaction between BF3 and NH3. BF3 is an electron deficient species because it has incomplete shell. With the help of this diagram, we can very easily understand that in BF3, boron has 6 electrons in its outermost shell. So it has incomplete shell. But if we look at the NH3, it has extra lone pair of electron. This NH3 will act as Lewis base. It will donate its lone pair of electron to the Lewis acid, that is BF3, and form a coordinate bond or acid Lewis acid base complex. Some other electron deficient species like AlCl3, cobalt 3 plus, Mg2 plus, etc. can act as Lewis acids because they can accept a lone pair of electron, while species like H2o, NH3, OH minus, etc. they can donate a pair of electrons. That's why they can act as Lewis bases. So the species which can accept an electron pair will act as an acid, and the species which can donate a lone pair of electron will act as a base. Now we will solve a question based on Lewis base theory. Classify the following species into Lewis acids and Lewis bases and show how these act as such. Number 1, OH minus. OH minus will act as Lewis base because it can donate an electron pair. F minus will also act as Lewis base as it can donate any one of its 4 electron pairs. H plus, that is a proton, will act as Lewis acid as it can accept a lone pair of electrons from bases like hydroxyl ion or fluoride ions. BCl3 will behave just like BH3. BCl3 act as Lewis acid as it can accept a lone pair of electrons from species like ammonia or amine molecules. Although Lewis acids and bases concept was able to explain, Arrhenius concept of acids and bases becomes useful in case of ionization of acids and bases, as mostly ionization in chemical and biological systems occur in aqueous medium. Strong acids like perchloric acid, hydrochloric acid, hydrobromic acid, hydroiodic acid, nitric acid, and sulfuric acid are termed strong because they are almost completely dissociated in their constituent ions in aqueous medium, they thereby acting as proton donors. So, if an acid is completely dissociated in aqueous medium, then we consider that acid as strong acid. Similarly, strong bases like lithium hydroxide, sodium hydroxide, potassium hydroxide, cesium hydroxide, and barium hydroxide are almost completely dissociated into ions in aqueous medium, giving hydroxyl ion. According to Arrhenius concept, they are strong acids and bases as they are able to completely dissociate and produce H3O plus and OH minus ions respectively in the medium. Alternatively, the strength of an acid or base may also be determined in terms of Bronsted-Lowry concept of acids and bases, wherein a strong acid means a good proton donor and a strong base means a good proton acceptor. Let's take an example. An acid Ha, when dissolved in water will be considered as base, then it will give H3O plus and A minus. H2O and H3O plus are conjugate acid base pair, and Ha and A minus are conjugate acid base pair. As acid dissociation equilibrium is dynamic, involving a transfer of proton in forward and reverse directions, on comparing the strength of two acids or bases involved in the dissociation equilibrium, we can find out the driving force behind the equilibrium. Consider the two acids Ha and H3O plus present in above mentioned acid dissociation equilibrium. We have to see which amongst them is a stronger proton donor. Whichever exceeds in its tendency of donating a proton over the other shall be termed as stronger acid, and the equilibrium will shift in the direction of weaker acid. If Ha is a stronger acid than H3O plus, then Ha will donate protons, not H3O plus, and then the solution will mainly contain A minus and H3O plus ions. The equilibrium moves in the direction of formation of weaker acids and weaker base because the stronger acid donates a proton to the stronger base. It follows as a strong acid dissociates completely in water. The resulting base formed would be very weak. Strong acids have very weak conjugate base, very important. Strong acids have very weak conjugate bases. Strong acids like perchloric acid, hydrochloric acid, hydrobromic acid, hydroiodic acid, nitric acid, sulfuric acid will give conjugate base ions like ClO4 minus, Cl minus, Br minus, I minus, NO3 minus, HSO4 minus, which are much weaker bases than H2O. Similarly, a very strong base would give a very weak conjugate acid. On the other hand, a weak acid like HA is only partially dissociated in aqueous medium. Thus, the solution mainly contain undissociated HA molecules. Typical weak acids are nitrous acid, that is HNO2, hydrofluoric acid, and acetic acid. It should be noted that the weak acid have very strong conjugate bases. For example, NH2 minus, O2 minus, H minus are very good proton acceptors and thus much stronger bases than H2O. Acid base indicator. Certain water soluble organic compounds like phenolphthalein, bromothymol, blue behave as weak acids and exhibit different colors in their acid and conjugate base forms, like HIN indicator is indicated by IN. When we dissolve this indicator, which shows color A in water, it gives its conjugate base which shows different color, that is color B. Such compounds are useful as indicators in acid-base titrations and finding out H plus ion concentration. Phenolphthalein is a very common indicator which we use in acid-base titration. This is the part of our practicals in class 11th. The ionization constant of water and its ionic product. Some substances like water are unique in their ability of acting both as an acid and a base. In presence of an acid, HA, it accepts a proton and acts as a base, while in the presence of a base, B minus, it acts as an acid by donating a proton. In pure water, one H2O molecule donates proton and acts as an acid, and another water molecule accepts a proton and acts as a base at the same time. The following equilibrium exists in this condition. H2O will act as an acid as well as a base. One H2O molecule will donate proton and convert into OH minus. These are the conjugate acid base pair, and another water molecule will accept that proton and act as a base. The dissociation constant is represented by, as we know that in dissociation constant we will write product upon reactant, so the dissociation constant can be given like this: K is equals to concentration of H3O plus multiplied by concentration of OH minus divided by concentration of H2O. As we know that concentration of water is constant, approximately constant, therefore when we multiply K with concentration of H2O, we will obtain a new constant, that is Kw, and the formula will be Kw is equals to concentration of H plus ion multiplied by concentration of OH minus. The concentration of H plus has been found out experimentally as 1 into 10 raised to the power minus 7 m at 298 Kelvin. And as dissociation of water produces equal number of H plus and OH minus ions, the concentration of hydroxyl ion will be equals to 1 into 10 raised to the power minus 7 m. Means concentration of OH minus ion and H plus ion will be same, and that will be is equals to 1 into 10 raised to the power minus 7 m. Thus the value of Kw will be is equals to 1 into 10 raised to the power minus 7 whole square. That will be equals to 1 into 10 raised to the power minus 14 m square. The value of Kw is temperature dependent as it is an equilibrium constant. Now we can calculate the concentration of H2o water at room temperature, that is 298 Kelvin. As we know that the density of water is 1000 gram per liter approximately, and its molar mass is 18 gram per mole. So molarity of water will be equals to 55.55 m. Therefore, the ratio of dissociated water to that of undissociated water can be given by 10 raised to the power minus 7 divided by 55.55, that is 1.8 into 10 raised to the power minus 9. Thus, the equilibrium lies mainly towards the undissociated water. We can distinguish acidic, neutral and basic aqueous solutions by the relative values of H3O plus and OH minus concentration. In acidic solution, the concentration of H3O plus ion will be greater than OH minus ion. In neutral solution, the concentration of hydronium ion will be equals to a hydroxyl ion, and in basic solution, the concentration of hydroxyl ion will be greater than concentration of hydronium ion.